we're going to look at irrational numbers, and we're going to start with just a definition. An irrational number is a number that cannot be represented by a fraction. And so, as I said in the previous video, it is a number that's defined by what it isn't, not the creation rule. But there are an infinite number of irrational numbers, and they pop up in different cases. E and pi are examples of special cases of irrational numbers, which we'll discuss more later. But the first place they come up with is square roots of particular numbers. And so I guess what we'll first look at is squaring numbers and then the gaps in those. So let's just make what we're going to call perfect squares. So we're going to take positive integers, we're going to take integers that are greater than 0, and we're going to square them. And we're going to see what the answers are. Well, we'll even do greater than or equal to 0. 0. So I'll give my original number, and then I'll square it. So 0 times 0 is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared, 4 times 4 is 16. I'm just going to continue where we're going to write some number and we're going to multiply it by itself. We'll get up to 2 gross here, or a gross. I'm sorry, 12 times 12 is a gross. A dozen is called a gross. I don't know where that name came from. And 13 times 13 is, 169. And I think I'll leave it there, mainly because I'm running out of room on the screen. And so these are perfect squares. And what that means is that if we write this thing called a square root, where the square root is a number such that n square root of n times square root of n equals n. So for example, the square root of 4 is 2, because 2 times 2 is 4, or 2 squared is 4. And we see that here. It's a way of going backwards in squaring. If we start on this side, what number gave us that? And so 36 square root is 6. And so numbers that are perfect squares aren't irrational. But look at the gaps in here. Right? There's nothing between 0 and 1, but we've got 2 and 3. 5, 6, 7, 8. 10, 11, 12, 13, 14, 15. And so this creates, in the gaps, irrational numbers. And we're going to look at those irrational numbers and how we can represent them. So for example, 2, because it's not a perfect square, the square root of 2, that's the best way we can write it. And it is irrational. Well, let's look at some other properties that we can attribute to square roots. And so the property we have kind of a first one coming out here, is that if I multiplied these two things, it gives me n squared, or n, well, sorry, not n squared, n, right? Because we said the square root of n times the square root of n equals n. And so if I multiply them together, I get the square root of n squared is n. Notice what happened here. The insides got multiplied together. Let's look at an example. The square root of 2 times the square root of 2 is going to equal 2 times 2, which is 4, or 2. So we can undo this thing by multiplying it by itself. This lets us do some neat things. For example, I'm just going to try to pick a random number here, 80, the square root of 80. Well, 80 isn't on my list, and it's irrational, but I want to write it in a more simplified form. So I look here and go, hey, 80 is here. So it can't have inside of it any of these numbers. They're too big. And so I come down here and I divide 80 by each of these numbers. Because what I want to do is I want to break it into two parts. And so I divide 80 by 64. Well, and I get a decimal, so it isn't going to work. I divide 80 by 49, and I get a decimal, it's not going to work. I divide 80 by 36, and then I get a decimal, it's not going to work. I divide 80 by 25, and I get a decimal, it's not going to work. But I divide 80 by 16, and I get 5. And so I can rewrite this as 5 times 16, which is nice because I can break these into two parts now. But I know 16 is a perfect square, and so I get 4 square roots of 5. And now I can write this irrational number in terms of this other irrational number. And this is something that we do with square roots or irrational numbers quite often. And we use it for finding things that aren't perfect squares. And so let's look at the perfect square factors. And so that's what we talk about, is we take whatever is under the radical and we check for any perfect square factors, and we do it in a descending order. So let me look at some of the examples from the text here. We're going to look at 75. Square root of 75. Well, I know that's a multiple of 25. 25 is a perfect square. And I know that I get 3 times 25, which means that this can break into two parts, the square root of 3 and the square root of 25. Well, I know the square root of 25 is 5, and so I write it like this. And this says I have 5 times the square root of 3, or I have a collection of 5 square root of 3's. Now what I kind of do about that, and I'm going to use the square root of 2 as an example. So the square root of 10 is equal to, well, not 10, let me go back one. The square root of 20 is equal to, well, I did my note. Give me 2 seconds. I wanted to use an example, and I do this sometimes. I'll try to pull an example out of my head, and I reverse my numbers. So I want square root of 8 is what I'll use. Because the square root of 8, well, that's 2 times 4, which is equal to 2 square roots of 2. This actually has a counterpart in reality. Remember when I said that the square root of 2 was the diagonal of that special triangle that had each leg 1. What I can say here is if these are the special square, and this is root 2 and this is root 2, then in the length of this big line is 2 square roots of 2. I'm using my irrational number as a measuring unit for it. And I think this is how these things first really got used by human beings as a tool, is because these triangle relationships were very useful in early engineering and design, and these real numbers really, really existed. Yes, I'm going to overemphasize real numbers really exist. And this became a way of measuring things. And so the mathematical technique we have that works with that is we find the perfect squares inside of them. And so we factor these into perfect squares. Now the way we do that is or at least the quickest way I do this, is you take this list of perfect squares, which I can keep creating. I can create another perfect square. What is 14 times 14? Notice someone doesn't have their calculator with them. 196, right? And if I take whatever my number is, like I did with 80, and I look at it, on my calculator I can divide, and the first thing I get that doesn't give me a fraction as my result, that's going to be the quickest way to do this. Other people will build factor trees, and they'll put together the perfect squares. Whichever methodology you see is best will help you solve these. I prefer writing the perfect squares and dividing my number by the perfect squares until I get something with no remainder, and then I choose that to simplify it. And that's a technique when I was tutoring I would show people to use. It's relatively easy to do in a test-like circumstance or quickly, if you have access to a calculator. If you don't have access to a calculator, then if we relook at what I did with 80, factor tree, so 8 times 10, 2 times 4, 2 times 5, 2 times 2, and so 1, 2, 3, 4. You grab pairs of things. So that's 4 times 4 times 5. And 4 times 4, well, the 4 comes out. And that's, I guess, the other thing that I'll point out is if you get the same thing times itself and it's leaving the square root, only 1 comes out. Right? 2 are inside, only 1 leaves. Some weird mathematical horror film context, right? Ha 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 ha. But that's how these square root work. And so we can multiply, we can divide, and we can simplify square roots. So from that rule that helped us find these, let's look at a multiplication rule. I can take the square root of 2, and I can multiply it by the square root of 5. And I guess a geometric concept of that would be, let's say I had one of those lengths that was the square root of 2, and I match it with another triangle that was square root of 5, but I build a rectangle out of it. And so now I have, a square root of 5 side and a square root of 2 side. Well, I know with rectangles, if I want to paint them, and since I'm on a computer here with a paint tool, let's see if this thing actually works on me today. I will literally paint it. Oh no, I painted everything I figured it would. That's because I left open my edges there, right? Let's close in my edges. See if that works now. There we go. If I want to know how much paint is in there, well, I multiply the sides. So I would need to multiply these lengths, which are really, really real lengths, even if I can't write it as a fraction. Well, the rule that we had for simplifying perfect squares also works here. So this is the same as 2 times 5, or the square root of 10. And I know this doesn't have simple factors, so I'm good. I'm done. I've got my number. But let's look at what happens if we have square roots that might be simplified. So let's look at the square root of 6 times the square root of 12, which is equal to 6 times 12 is 72. But 72 might be able to be simplified. So I run back out and I look at my list of perfect squares, and I divide 72 on the calculator by all of these, right? And so what do I get? Let me see if I can find my calculator here so that I can do this verbally. All right, so here's my calculator. Let me turn this on here and show you what I mean. So we'll get this started. Clear out of that, and we'll pop over here And so I'm going to use 80 as, what was the number? No, 80 wasn't my example I had. What was the number I was working on? I'm working on 72. So I'm going to take 72 and I'm going to divide it by each of my perfect squares. So I'll come here and let me get the calculator back on. And unfortunately, my list of perfect squares vanishes on the screen here from you guys, but we'll make it work. So 72, well, is smaller than 81. So my first perfect square is 64. So divide it by 64, and I get a fraction. So it's not going to be a multiple of that. Take 72 and I divide it by 49, and I get 1.4. Nope. So I keep going. My next perfect square is 36. And hey, 2 times 36 is 72. So that's the one I'm looking for. So let's use that. So let me scroll down here. So this is equal to 2 times 36. And I know 36 is a perfect square, so this is equal to 6 square roots of 2. So even though multiplication can put these together, I can use my perfect squares to write it in the most simplified form. Now there's another way we can do this also. The nice thing about multiplication is it doesn't matter the order we do multiplication in, and so we could actually do this trick first and then multiply the things inside and outside. So let's take this here, and we get 2 times 3 from the first one, and we get 3 times 4 for the second one. Now 3 times 4, that's going to give me 2 square roots of 3, and this gives me 2 times 3. So I'll put the 2 out front, and now I'll multiply these together. That's going to give me 2 times 3 times 3. But 3 times 3 is a perfect square. So I'll pull the 3 out front, and I get, whoops, not 3, 6. I get the 3's come out front, so they're gone from in here, and I'm left with 2. That gives me 6 root 2. That's one way of doing it. This is another. I actually prefer this way of doing it, but you have to get used to every time you see 2 things, throw it out front. And that's just a different way of thinking altogether, right? But they're valid ways of thinking. The numbers do their patterns underneath it, and then we follow the way of thinking. Well, the other thing we can do is we can divide. Okay, because multiplication and division are linked, we can divide radicals. And so the idea of 25 divided by 9 square root is the same as the square root of 25 divided by the square root of 9, which is 5/3. And so what we say mathematically is the square root of a over b is the same as the square root of a divided by the square root of b. Now this can also work 2 ways for us. Right? I split apart a fraction to get it. I can also make a fraction come together. I can take the square root of 75, and divide it by the square root of 3, and I can now blend these together so that 75 is divided by 3 under the square root, which is equal to the square root of 25, which is equal to 5. Remember, these rules we do are reversible. So I can take everything under the square root and split it apart. Or I can take everything that is separated and put it together. And it depends on which is going to simplify things for me. I guess that's part of where we start getting artistic with mathematics, is we look at what we have and go, would the pattern be nicer going in this direction, or is the pattern more simple in this direction? Well, let's look at doing this another way. So if I retake the square root of 75 here over the root 3 and realize I could put it together and I get 5, let's say I didn't put it together. Let's say I take 75 and I simplify it. So I know that 3 times 25 is 75. Well, I know this is a perfect square, so I'll bring the 5 out. But notice what I get here. I get a number divided by itself. And any number divided by itself is 1. And so I get 5 also. And so these rules are not the only directional way we can move. And we want to start seeing that these patterns that we use to assemble numbers and operate on numbers lead us to the same places if we follow them. If we follow the rules, we get the same result, no matter which direction I take. Well, I already said that we could use these things as if they were measuring rods. And so we get another rule where we can add or subtract them. And so if I have a square root of c plus b square root of c, this says I have a of these things and b of these things. But if these are the same thing, then altogether, that's the total of them I have. And the same thing works for subtraction. If I have a of them and I take away b of them, that's how many I have. Notice I'm starting to do a language thing here. I'm talking about multiplication, saying how many times I have something. And times is the word we use for multiplication. But if the thing I'm multiplying is the same thing, I can talk about it in terms of the quantity of that thing I have. And we do this for many different mathematical quantities, is that word structure works the same and that pattern works the same. So this is what this looks like if, again, I'm using 5 square roots of 2 to measure something, and I add 2 more square roots of 2 to it. Well, I have 5 of them, and 2 of them, I have 7 square roots of 2 altogether. And hey, that's reversible. If I have 7 square roots of 2 and I'm going to take away the 2, well, that brings me back to the 5 square roots of 2. And I'm focusing on how many of these things I have. But they have to be exactly the same for me to do that. And so a neat thing can happen is we can blend these rules together. So I can have the square root of 20 minus the, let's see, square root of 20, and the square root of 5. Now 20 is equal to 4 times 5. And so that's 2 square roots of 5 minus a square root of 5, or 1 square root of 5. So notice how this process chained all of the things we did together to simplify this into a smaller atomic structure, right? These are the same thing, but this will be easier to give us value or meaning to it. And the last thing we want to look at with radicals is a way that we talk about radicals. When I write the fraction 1/3, I might not know exactly what the value is until I run to a calculator and see that it's 0.333 repeating. But I know that 3 is bigger than 1. And I know that 4 is bigger than 3. So 3 divides 1 into less pieces. So it's the bigger number. I can compare fractions by knowing what the denominator does. But if for some reason I get a radical in the denominator, I don't visually get an idea of what it is. And so we tend to say, hey, we don't want radicals in the denominator. We don't want square roots in the denominator. And so what we say is what we want to do is we want to rationalize the denominator. And we're going to use two rules to do this. We're going to realize that if I multiply a square root by itself, it gets rid of the square root. And if I multiply any number by the number 1, I don't change the number. And when I put these two tricks together, I want to multiply this by the square root of 5 to rationalize the denominator. But to not change the overall number, I need to multiply it by 1. And that's a way of writing 1, because anything divided by itself is 1. And so I get upstairs the square root of 5, and downstairs the square root of 5. And this is a convention that mathematicians use instead of writing square roots in the denominator. And I spent years learning this in algebra classes, and then in pre-calculus classes and trigonometry classes, having to rationalize the denominator. And somewhere around upper level calculus, mathematicians give up. And you start seeing this written because the numbers get odd. And so this is a convention. And the reason this was a convention was these were easy for people to remember a few of them off the top of their head. I still remember that the square root of 2 is approximately 1.414, and then it starts doing things that don't repeat. And so occasionally in trigonometry we see square root of 2 a lot. And so I could look at square root of 2 over 2 and go, oh, that's this divided by 2, which is, let's see, 7 goes into that 0.7, 1, 4, 0, bring down another 4, another 7, right? And so this relationship comes out in trig a lot, but we wrote it like this so we could easily estimate it. Remember how estimation was an important thing here. Now that we have calculators, this isn't as important as it used to be, but it is still a good convention. And once you play with these a bit, having a consistent denominator that's a rational number, you'll find to be easier to work with. And so that's why we practice the skill of rationalizing the denominator. All right, this is the section 4. Play with the homework in section 4. Email me if you have any questions. I can record specific examples if you bring them to me as a question. Remember, in Pearson, there's the Ask My Professor down at the bottom of Pearson. On the help, you can ask my professor, and I'll tend to record little videos about the questions people are asking. If you don't ask anything, I won't record anything extra, right? Saves my time and your time. You don't have anything extra to watch. But I'll add them up to our little YouTube playlist if anyone has any questions. Right? Keep studying, keep reading, and keep asking yourself, what can I do with these things? Until again.